Today, it's nothing new besides a little bit of position, velocity, acceleration. But we're just going to really make sure we understand all that we've done so far, how it helps us understand what's going on with our original function, and we are going to be able to determine the shape of a function. Okay? Because we now know we have these situations. If you're decreasing concave up, we'll understand that the shape of your function looks like this. Increasing concave up, here's our shape. Increasing concave down, decreasing concave down, increasing no concavity, decreasing no concavity, neither increasing nor decreasing no concavity. Okay? And what we're going to do is we got a number line analysis for f prime. We can do that. It's already done for us. We have a number line analysis for f double prime. We're going to throw another number line down. Why not? Okay? Only this is going to be the shape of f. And on this f number line, you're going to include all of the critical points for f prime and f double prime. And then on your intervals, you're going to be able to sketch the shape of that. So if I know f is going down while f is concave up, I know that f is going to look like this. Decreasing concave up. If f is going up and is concave up, f will look like that. If f is going up and is concave down, it'll look like this. If f is going down and is concave down, it'll look like this. Going down, concave up, back to where we started. Going up, concave up. Okay? And you now can understand what the graph of f's shape looks like. Now, where are the y locations in this situation? I don't know. It doesn't really matter. I'm just understanding the shape of f, but we could do a better job if we were given a function, which we will in the future. Going down, concave up, going up, concave up, going up, concave down, going down, concave down, going down, concave up, going up, concave up. Min here, max here, min here, point of inflection here and here. Okay. Now, I produced the notes and then I changed some things. So this is one example of when what's on the board is different from your notes. Please replace your graph with my graph. And now I'm going to give you the graph of f prime, and I want us to accurately sketch what f looks like. Maybe to the right where you have space, you're going to produce your three number lines. One for f prime, one for f double prime, and one now for the shape of f. Okay. This is exactly what you did in your quiz. Produce f prime and f double prime. Now we're going to be able to sketch the separate portions of f. It's important to understand the zeros for f prime and the zeros for f double prime. Where are your zeros for f prime? At -1 and at 2. Where are your zeros for f double prime? -1 and 1. It will help us, and we've done this so far, making sure things are like aligned so that, you know, -1 is to the left of 2, not on top of 2. F prime values are positive, then 0, then positive, then negative. F double prime values would be negative, then positive, then negative. From there, we know what that tells us about f. Going up, going up, going down. Then that tells us f is concave down, concave up, concave down. I'll throw down all three of those points, -1, 1, and 2. Now understand what the graph of f's shape is. Okay, go ahead and sketch those little portions of the graph of f if you haven't done so already. Going up, concave down. Going up, concave up. Going up, concave down. Going down, concave down. Exactly where it goes doesn't matter right now. In the future, we'll understand exactly how much we're going to be going up and going down. For right now, we don't really care. We're going up, concave down, going up, concave up, going up, concave down, going, wait, hold on, I messed up. Going up, concave down until -1. Between -1 and 1, I'm going up, concave up. Between 1 and 2, going up, concave down after 2. It's like that. We have a point of inflection here. It's neither a max nor a min. We have a point of inflection here. We have a max here. We do not have a min. Okay, let's do one more just like that. Here is the graph of f prime. This is the same as yours. Go ahead and accurately sketch f. The shape, accurately sketch the shape of f. Okay, now, is this exactly what f is going to look like? Well, we don't know right now. In the future, we will. At least we'll know how higher the max is compared to the min. We'll know how much higher the point of inflection is compared to the min. For right now, this is the best we could do. It's just like, this is what the shape is. You know, could you have drawn this differently? Sure. I could have like said, oh, maybe I'm going all the way down here, up a little bit, and then maybe up a lot, and then down like that. Like, you don't know that. Okay? For right now, you don't know that. As long as you understand the shape. But and given the graph of f prime. But what we will know is exactly what a function will look like if I'm given the expression for the function, if I'm given what f of x is equal to. Now, I can do a fantastic job sketching what this looks like, where the max is, where the min is, where the point of inflections are. Okay, I can even do a little bit more analysis. And if I asked you to do this before you learned calculus, you would just start plugging in x's, or you'd hope that you had a calculator nearby. But if you don't have your calculator, now with calculus, we can do a very, very good job, without the use of a calculator, sketching what x cubed minus 3x squared plus 3 looks like. Because you can do an analysis of f prime, you can do an analysis of f double prime, you can understand the shape of f, and we can do what probably we would have done before calculus. We can understand some interesting points on the graph of f. Okay, let's go ahead and do our analysis of f prime and our analysis of f double prime. Once we have all of that information, the shape, and some interesting points, we're going to do a great job sketching f. And this, my friends, is like the culminating type of problem from this unit. We won't see many of these problems that used to be bigger on the AP test, is like accurately sketching a curve. And it's a very common thing to do in Calculus 1 classes in college. They will, on a test, say, like, accurately sketch this function. You have to do this entire analysis, okay? But not something that you see on the AP exam much anymore. That's how I'll put that away. Do this problem. Do your sign analysis. If I pull out 3x from 6, do I get x minus 6? What's 6 divided by 3? So that should be a 2 right there. So you should have 0 and 2, not 5 and 6. 0 is a solution. We get 0 and 2 for f prime. We'll get positives, negatives, and positives. For f double prime, I'll get 1. And we'll have positives and negatives. This is very standard, very simple, this type of function. It's sign analysis for f prime and f double prime. Plop all three of those down. If f prime is positive, f is going up, but we are up and concave down, up and concave down, down, concave down, down, concave up, up, concave up. So I understand that's going to be the shape of f, and we are going to focus around 0, 1, and 2. So if I can kind of slide this over a little bit. But let's find the actual point locations at 0, at 1, and at 2. We'll call those interesting points. We could plug 0, 1, and 2 into our function and find out the exact locations of the y-coordinates of our maxes, mins, and points of inflection. Because I know I have a max at 0, I have a min at 2, I have a point of inflection at 1, but exactly where it is located I can now worry about. Where am I plugging things into? My original function, right? To find the points. Go ahead and do that. Do it. Don't wait. Do it. Don't wait around for me to do it. It's not going to help you. You get better through struggling. If you don't struggle, you'll never get better. Eight minus 12, negative 4, plus 3, negative 1. I have the point 0, 3, 1, 1, 2, negative 1. Great. If I plotted those 3 points, you'd probably try to connect them with a straight line. So you probably know what an x cubed graph looks like. But now we know we are increasing, concave down, decreasing, concave down, decreasing, concave up, increasing, concave up. What are some other interesting points that I would possibly try to find? Not at 0, 1, and 2. Yes, the zeros. If I wanted to do an even better job, I would find the zeros. Don't try to find the zeros. Okay? But let me just show you, my friends, the power of what you just did. And this is what was how people graphed functions before the use of a graphing calculator, is they understood calculus. Okay. 0, 3, 1, 1, 2, negative 1. Here's my shape, exactly like I have, maybe not to scale. This is not to scale at all, because this is going from 0 to 5 here. This is 0, 1, 2, 3. So that's it. We got it. Okay. We will complete notes after lunch during Genius Hour. We're going to switch gears. We've kind of done an all-encompassing question where we are able to accurately sketch a function based on signs of derivatives and second derivatives. We're going to shift gears to our physics application of derivatives with position, velocity, and acceleration. Okay, and we will find that we will be able to answer questions pertaining to when things are increasing or decreasing, and we'll start talking about speed, okay, by looking at signs of derivatives first and second. Okay, first question I have, and this is different, this function, than what's in your notes, so please change the one in your notes to the one that I have. I'm asking you if some object follows a position given by x of t, is the velocity of this object increasing or decreasing at t equals 1? Now, the first thing we need to know is that I'm not asking you for, like, when is the velocity of max, or when is the velocity of min. So I do not have to, since I'm only focusing on one location, this is important, since you're only focusing on one location, you do not have to do a full-on sign analysis. Of like x prime or x double prime. Like, this is not necessary, because we can just look at values that would help us answer this question at 1. Okay, so not necessary. I'd like you guys to try to figure this out yourself. Is the velocity of this object increasing or decreasing at 1? So go ahead. First instincts, without doing a number line. Go ahead.
I forgot to get it up to you.
To review, there is going to be a video.
Okay.
So watch that video.
Okay.
Okay, now we need to remember from Unit 3 that the derivative of position gives us velocity. And then the second derivative of position, the first derivative of velocity, gives us acceleration. Okay? Most people's instincts are to take the derivative, and they get t squared minus 8t plus 7. And the first thing that they think about doing is plugging in 1. Anybody else get that, have that instinct, right? And you plug in 1, and you get 0. What does that mean? That's what it means. It means that the object is not moving right now, at this moment, okay? Does that say anything about if my values are increasing or decreasing at 1? No. And you might be like, yeah, it's at rest, so it's neither increasing nor decreasing. But you're not thinking about it the right way if you think about that. We could pass through a 0 at 1 and be increasing. We could pass through a 0 at 1 and be decreasing. Okay? So let's go back to the concept. And if you go back in your notes, use Miss Doris' note packet as an example. You go back to your notes to lesson 2. Right here. Something is increasing if what? Its derivative. The key word is its derivative. Its derivative is positive. Something is decreasing if its derivative is negative. Now, that's not the derivative. Everybody thinks of the derivative as like the first derivative. And you're like, oh, this is the first derivative, but this is 0. I'm not increasing or decreasing. No. Something is increasing if its derivative is positive. Something is decreasing if its derivative is negative. So finding that the velocity is 0 at 1 actually means nothing when it pertains to the question. Find the answer to this question now. Let's be on time to Genius Hour, please. Okay? So, we would have to look at the derivative of velocity. Now, the derivative of velocity is acceleration. I actually don't care. When it pertains to this problem, I'm just going to look at the sign of the derivative of velocity. And the derivative of velocity is 2t minus 8. And since I'm only worried about what's going on at t equals 1, you plug 1 in here, you get that it's -6, but actually I don't even care that it's -6. It's not asking you for the actual value, it's just asking you, are we increasing or decreasing? And since v prime at 1 is negative, we therefore can say velocity is decreasing. Why? If I ask you for justification, because its derivative is negative. At t equals 1. Now, some people might not get there. Some people might not get to this point of saying, oh, I have to take the derivative of velocity. They might stop here at v of 1 is equal to 0. But then they might think like, oh, well, that's not telling me if my values are going down or up at 0. So they then do something else. They plug in 0 into my velocity. They get 7. They know that at 1, they get 0. And if you plug in 2, you get 4 minus 16 plus 7, so it's -12 plus 7, which is -5. And then they say, oh, Mr. Messner, you want justification? Here's my justification. My velocity must be decreasing. Right? Decreasing in values, going down in values. I go from 7 to 0 to -5. I'm going down. Does that make sense? Now, if this was not a calculus class, this would probably be sufficient. But this is a calculus class, so I would not accept this. Why wouldn't I accept this? Well, why not? Why isn't that the right thing? I'm showing 7 to 0 to -5. I think the values are going down. I got the same answer, right? But why is this not acceptable? That's exactly right. Mr. Kilgall, I do not know what's happening between 0 and 1. A lot can happen between 0 and 1. Okay? To be certain, I'd have to check at the 0.99999 second and the 1.00000 first second to make sure that my values are going from positive to 0 to negative. Okay? So this would not be acceptable. However, I would accept some sort of analysis like this, but I don't want you to do it. If you ended up setting this equal to 0, and I asked you, okay, same question, and you went ahead and did a number line analysis like this. And you got 7 and 1, and you knew that that was all of the zeros. And you threw down 1 and 7. You got a 0 here, a 0 here. And if you realize that the velocity values are positive to the right of 7, negative between 1 and 7, and positive to the left of 1, then I would accept this. Okay? Because you said, okay, my values are positive to the right, to the left of 1. They are 0, then they are negative to the right of 1. My values must be decreasing. I'd accept this. But what if I asked you, is the velocity increasing or decreasing at t equals 5? Do you know if the values are going up or down at 5, looking at a sign analysis? You know that the values are negative, but are they negative and going down? Are they negative and coming up? This would not work at any other value besides a 0. So what would you have to do? What we did the first time around. You would take the derivative and see if it's positive or negative. So if I plugged in 5 in here, would I get a positive or negative? Positive. So at t equals 5, is the velocity increasing or decreasing? Increasing. Does that make sense? We are in calculus class. We will use derivatives to explain things, because derivatives tell us a lot. The value of a derivative tells me if the original thing is increasing or decreasing. Is it going up or going down? I ask you, is velocity increasing or decreasing? Look at the sign of its derivative, the sign of v prime. Okay? So, remember that concept. Write this down again. Circle this question. This concept is vitally important in this class. Okay? But another application with position, velocity, acceleration, and looking at the signs of position, velocity, acceleration, or actually just the signs of velocity and acceleration, is when we discuss speed. Okay? Now we know speed is velocity without direction. It's the absolute value of velocity. It's always positive. And it's velocity without direction. Okay? Now, know that velocity does have sign. If velocity is negative, we would say the object is traveling to the left or down, depending on what type of axis you're looking at. Velocity is positive. The object is traveling to the right. We know velocity is 0. The object is at rest. Now, when is something speeding up? What comes to mind when you talk about speeding up? Discuss with your neighbors. What comes to mind when you talk about speeding up? Okay? First thing that comes to mind with speeding up is acceleration, right? You need to have acceleration to speed up, okay? But a lot of people think, oh, if acceleration is positive, you have some acceleration, you're speeding up. It's actually not the case, okay? But acceleration is important. Now, I'm going to use my friend here to hopefully help you see when something is speeding up or slowing down. Okay, so anybody see this guy before? Oh, he's a great guy. Okay, now let's say this guy has a positive velocity. Don't worry, this guy's great. Okay, now there's no acceleration, just velocity. He's moving constantly. He's not speeding up. Cool? Great. Hold on, let me show the velocity vector. That way you can kind of see it. If my guy has a negative velocity, you can see he's moving to the left, but he's not speeding up. Good so far. Okay. Now we need acceleration to speed up. Okay. So I'm going to give this guy a 0 velocity, but he's going to have some acceleration, which means his velocity values are going to be increasing, right? The derivative of velocity, acceleration. So if acceleration is positive, velocity is increasing, as in going from 0 to more positive values. You can go from negative values and less negative, and that's increasing anyways. But now we can see my guy is speeding up. You good with that? You saw him speed up. Okay. Now I can start here and give this guy some negative acceleration, and you can see he is speeding up to the left. Do we see how he is going faster and faster? Okay. Now I'm going to just do something with both, with acceleration, but I'm going to move the acceleration vector from the right to the left, okay? Just back and forth. And we should be able to see, looking at the green arrow and the red arrow, when my guy is speeding up and when my guy is slowing down. I'm going to say out loud when he's speeding up and when he's slowing down. And I want you to look at the direction of the arrows, okay? All right, so here we go. Our guy is speeding up to the right. He's slowing down, stop. Speeding up to the left, slowing down, stop. Speeding up to the right, slowing down, stop. Speeding up. Don't just laugh, think. Speeding up, slowing down. He has stopped. He's speeding up. Let me do a better job. Slowing down, stop. Speeding up, 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 slowing down, stop. When is my guy speeding up? When is my guy slowing down? Discuss with your neighbors. You think you need another demonstration? Do I need to do it again? No, I'm not going to do it again. That'd be funny. Who's got it? When is something speeding up?
When the acceleration and the velocity have the same sign.
Yes. When the arrows are pointed in the same direction. Speeding up, the arrows are going in the same direction. If I started like this and the arrows are in opposite direction, we are going to be slowing down until we've come to a stop. Okay? And then my velocity values, which are decreasing, are going to be going in the same direction as my acceleration, and we will be speeding up. My arrows are going in the same direction. Opposite directions, slowing down until we've stopped. same direction, speeding up. Does that make sense? Okay. So when is something speeding up? Velocity and acceleration are going in the same direction or have the same sign. When is an object slowing down? When the velocity and acceleration have opposite signs. Or have opposite directions. Opposite signs. Now, remember the relationship between position, velocity, and acceleration, okay? Position, its derivative, velocity. Position, second derivative. The first derivative, velocity, acceleration. I'm going to show you, and this guy also does a good job of showing us everything that we've been talking about, okay, in class so far. This is the graph of what I just did, my guy's position, his velocity, and his acceleration. Okay? Now, we can look at portions of this graph. Okay? So my guy started out at a position of 0, and then his position started moving here. So that means he was moving to the right. Okay? Now, the derivative of position, velocity. My velocity is positive when I'm moving to the right. Now, all of a sudden, he maxed out at a position of like 10, and he started moving to the left. Well, the slopes of my position, my velocity values right here go from positives to negatives. So I'm going to the right, then my velocity values start decreasing. I'm still going to the right. Now I'm moving to the left. Then all of a sudden my velocity values, I start slowing down. My velocity values start increasing. I've come to a stop. I start moving to the right. Velocity value is positive. I eventually come to a stop. Okay, I'm moving to the left here. My velocity values are negative. Isn't that cool? We can see, well, I was moving with a positive velocity, okay, consistently, this slope right here. Then, all of a sudden, my acceleration changed to a negative value. The slope became negative and consistent. Then, I changed the acceleration to a positive and consistent value. My slope was positive. Isn't that cool? So we can see how the graphs of one gives us the graphs of the other. If you look at the slopes of this, you get this. If you look at the slopes of this, you get this. Now, another thing we can see, when my acceleration is positive, okay, what is the relationship between acceleration and position? What's the relationship between acceleration and position? Second derivative of position is acceleration. Now, what did we learn from last class about the second derivative sign? Concavity, okay? So, when a second derivative is positive, my original function is concave up. Here is a positive second derivative. What do we see about the graph of my original function? Concave up. And then, boom, we move to a negative acceleration. Well, right here is when we move to a negative acceleration, we're concave down. Then we move to a positive acceleration, starting right here. Well, we switch to concave up, okay? So this is all seen with my guy. And I can kind of start over and show you that here, starting with 0, starting with positive, my dude, is right there. Okay, here we go. Show the vector, show the vector. That's going to be big. We need to zoom in. Okay, here we go. I'm going to change acceleration. It's going to change the graph everywhere. Positive, negative. Slowing down, speeding up to the left, slowing down. Speeding up to the right, slowing down. Stopped, speeding up to the left. Isn't that great? Okay? We can see the sign of our second derivative, concavity. We can see the slope tells me of this, tells me the direction. The slope of this tells me the acceleration, if my velocity values are increasing or decreasing. My velocity values go from 0, stop, they're positive, but then they get less positive. We can see we are speeding up here, we are slowing down, speeding up, slowing down, speeding up, slowing down, speeding up. We can play back. Speeding up, slowing down. Stop, speeding up, slowing down. Stopped, speeding up, slowing down, stopped, speeding up. Okay? It's all about derivatives. Beautiful. Now, if I gave you a velocity graph, you should be able to figure out by looking at the velocity graph whether or not you're speeding up or slowing down. But I don't want you to do that. What I want us to do is what we've been doing in class so far, which is looking at signs of derivatives. So the sign of velocity and the sign of acceleration. So if we go to our first example here, this is different than yours, get rid of the negative. I say, okay, here's the position of a particle. When is the speed increasing? When are we speeding up? I want you to do what you've been doing so far, which is figure out when the signs of velocity, which is the first derivative of position, when are they positive, when are they negative, do a sign analysis of velocity, and then do the same thing for our second derivative, which is our acceleration, or the first derivative of velocity. You've done that, okay? Only I would say this is f, and I'd say when is this f prime positive, and when is f double prime positive, et cetera, et cetera. Only now I'm just doing it with position, velocity, and acceleration. I want you to tell me when we are speeding up. Yeah, change it to positive. Okay, do the sign analysis, and then we'll make sure we have the correct answer and make sure we understand why. Now, there's so much information you can get from just a sign analysis. This is telling you that my object is moving to the right, then to the left, then to the right. You know, that's one thing. Or you could say my position is increasing, then decreasing, then increasing. The acceleration can tell you that your position is concave up or concave down, which is talking about like essentially speeding up or slowing down, but based off of your velocity. When is something speeding up is when the signs agree with each other. Here, I am speeding up to the left. Here, I'm speeding up to the right. Okay? You can speed up in both directions. Just check your signs of things. Okay? Let's go to this one next, and we'll finish off the last one. This is the graph of velocity. When the velocity is positive, I'm moving to the right. When the velocity is 0, I've stopped. When the velocity is negative, I'm moving to the left. Tell me, and let's just talk about when the speed is decreasing. When speed is decreasing, we're talking about slowing down. That's an important thing to know. Okay? When is this object, this particle, slowing down? Now, you could just look at the velocity graph and figure it out if you kind of think about the guy and his movement. However, I'd rather you just do what we've been doing and create a sign analysis for V and A, knowing that V is like X prime. And when you're given V, that's like being given X prime. You can think of it as being given F prime. Okay, so I'm giving you F prime. And you can look at the values of X prime. Then to figure out A, that's like figuring out X double prime. That's the same as looking at the slopes of F prime, or the slopes of V. Okay, do your sign analysis and compare your answer with a neighbor. You don't have to plot all of the values down. I would look at the zeros for V. I'm starting at a 0. I have a 0 at 2. And I have a 0 at 4.
Yeah, wait, we got it right now.
The answer is from 1 to 2 and from 3 to 4. Let's make sure we're comfortable with this. This is like I'm giving you the graph of f prime. Well, this is the graph of v. When is v 0? It's 0 at 2 at 4. V is positive between 0 and 2. V is negative between 2 and 4. V is positive after 4. If we have all of our zeros, our signs will all agree with each other in between our zeros and outside of our zeros. If I look at A is the slopes of V. Okay? The slopes of V are 0 at 1 and at 3. So I plot 1 and 3 down. The slopes of V, which gives us values of A, are positive until 1. Negative from 1 to 3. Positive after 3. When is speed decreasing? Speed is decreasing when the arrows are going in opposite directions. I'm moving to the right, however, my values are decreasing, which means my acceleration is to the left. I'm moving to the left, but my acceleration is going to the right, which means my values are increasing from negative values to less negative values, from positive values to more positive values. Who knows? Actually, we're going from negative values to less negative values. So when those signs don't agree with each other, that is when I'm slowing down. Questions? Okay. This question. Now, read the question carefully. Am I asking you for the intervals in which the object is speeding up? Am I asking for the intervals in which the object is slowing down? No. Do you need to do an extensive sign analysis for V and A? No. Because you are just concerned about what is going on at this one point. Okay, answer the question. Are we speeding up or slowing down at 2/3? Now, if you took the derivative, first of all, you got to understand there's an outside and an inside. So you got to use the chain rule. The derivative of the outside is cosine, the derivative of the inside is pi. If you got V prime, which equals A, is cosine of pi t times pi. And if you plugged in 2/3, you got the cosine of 2 pi over 3 times pi. The cosine of 2 pi over 3 is -1/2. You got negative pi over 2. And you just looked at this value and you said, oh, the acceleration's negative. I'm slowing down. You didn't do enough work. You got to figure out, is the acceleration negative and the velocity positive? If that's the case, then you're slowing down. But if your acceleration negative and your velocity is negative, we know we can speed up going to the left. So this is not sufficient. You need to look at your velocity at this moment as well. Just like we did both number line analysis for velocity and acceleration, I can't just stop here. This is not enough. All you need to do is plug in 2/3 into your velocity to figure out that this is √3/2, which is positive. This is negative. It is because my velocity is to the right and my acceleration is to the left that we are slowing down. It's not because my acceleration is negative that I'm slowing down. It's because the vectors, the arrows, are going in opposite directions. We are slowing down, not because acceleration is negative. You can speed up with a negative acceleration. You are slowing down because V and A have opposite signs. How do I go back? I don't want to start again. Reset. Okay. Negative acceleration could be speeding up. Negative acceleration could be slowing down. All about the signs of both. Okay? Beautiful creation of the relationship between position, velocity, and acceleration, looking at slopes. All right? All right.